everyone. We are continuing in this third and final video to study second order systems and mechanical applications. And our focus here will be on including an external force to the system. Let's start with a quick review of where we've been so far. So the goal of this section is to investigate the oscillations of typical mass and spring systems having 2 or more degrees of freedom. And this figure shows 3 masses, for example, that are connected to each other and to 2 walls by the 4 indicated springs. We showed that if we combine Hooke's law of force with Newton's law of force to the 3 masses, it yields the following equations of motion. We then wrote this system in matrix form. The matrix M we refer to as our mass matrix. It's a diagonal matrix with the values of the mass down the main diagonal. The matrix K we call the stiffness matrix. It includes the information about those springs. And then our X is, of course, our displacement vector. Now, in our last video, we considered the following example. We had a mass and spring system shown in the figure with stiffness matrix given here. We were asked to find the 2 natural frequencies of the system and describe its 2 natural modes of oscillation. So to solve this problem, we started with our basic equation, which in this example became our mass matrix, was that diagonal matrix with our values of our mass down the diagonal, so 1 and 2. And then the matrix K was given according to our formula and the values of K1, K2, and 3 that were given. We solved this system and found these 2 solutions, x1 and x2. And then we're able to conclude that in the natural frequency of omega equals 1, the 2 masses moved in the same direction with equal amplitudes of oscillation. And that in the natural frequency of omega equals 2, the 2 masses moved in opposite directions with amplitudes of oscillation of mass 1 twice that of mass 2. Okay, so here we go. In this video, we now want to turn our attention to the case when one of the masses in our mass and spring system is subject to an external force in addition to the forces exerted by the springs attached to it. So in that case, our homogeneous equation mx double prime equals kx will be replaced by the non-homogeneous equation mx double prime equals kx plus f, where this f is the external force vector for the system. Now recall that matrix M is a diagonal matrix. Its determinant will be non-zero since none of our masses are 0. And since it's invertible, then we're going to multiply both sides of this equation by M inverse. So multiplication by M inverse yields that x double prime equals M inverse times kx plus f. Or to simplify notation, we can write it as x double prime equals ax plus f, where little f here is the external force vector per unit mass. Now, we're especially interested in the case of a periodic external force, where this little f is some constant vector, capital F naught, times cosine of omega t. And in this case, we're going to anticipate a periodic particular solution, a particular solution x sub p of some c, some vector c, times the cosine of omega t, with the known external frequency of omega and with a coefficient vector of c to be found. So let's put this together. So we have a differential equation, x double prime equals ax plus f. We're assuming we've got an external force of f naught equals cosine of omega t, and we're making a guess of a particular solution to be some vector c times cosine of omega t. And we're going to see in what cases this particular solution will in fact solve our differential equation. So we're going to substitute our particular solution into our differential equation. So our differential equation becomes our x double prime will be minus c omega squared times cosine of omega t. we have equals A times X, which is C cosine of omega t, plus our force F that we're assuming to be capital F naught cosine of omega t. Okay, now we can clean this up really easily because we're assuming that we do in fact have an external force and therefore that cosine of omega t is non-zero. So we can cancel the cosine of omega t's and rearrange this equation a little bit, and it will become minus F naught equals A plus omega squared I times the vector C. Okay, now observe that this matrix, this A plus omega squared I, is non-singular, so we can solve this equation for C unless that negative omega squared happens to be an eigenvalue of the matrix A. So, in the big picture then, we therefore say that a periodic particular solution of the form C times cosine of omega t will exist provided that the external forcing frequency, the omega here, does not equal one of the natural frequencies, omega 1, omega 2, or omega 3 of the system. Now, in the case when the omega is one of the natural frequencies of the system, this corresponds to the phenomenon of resonance, which we discussed back in chapter 5. So here's our big picture slide. All right, so suppose we have a non-homogeneous system. We've got an external force. So our force system looks like x double prime equals ax plus f cosine of omega t. Then in that case, our solution will be xc plus xp, where xp is a particular solution of the non-homogeneous system, and xc, our complementary solution, is a solution of the corresponding homogeneous system. So just like back in previous chapters when we were solving non-homogeneous differential equations, we first solve the homogeneous and find the complementary solution in that case. We make a guess for a particular solution and then add the two together, right? And in this case, where our guess for our particular solution is that it's going to be some vector c times the cosine of omega t. That's what our guess for our particular solution is going to look like. Okay, let's do the example. All right, so we've got the mass and spring system from our previous example. We suppose the system is set in motion from rest, meaning the x1 prime of 0 and x2 prime of 0 are both 0, and that it's set in motion in its equilibrium position, meaning that x1 of 0 and x2 of 0 are both 0. Suppose we have external forces, f1 of t equals 0, f2 of t equals 120 times the cosine of 3t. And these are acting on our masses m1 and m2 respectively. Let's find the resulting motion of the system and describe it as a superposition of oscillations at 3 different frequencies. All right, so we start with our equation, mx double prime equals kx plus f. For this example, remember our mass matrix will be that diagonal matrix. The entries on the diagonal are the values m1 and m2. Then we've got our matrix K, which is given to us in the problem. And we've got our external forces. We're told that F1 is 0 and F2 is 120 cosine of 3t. Okay, so the first thing we have to do is to solve the corresponding homogeneous system. But we solved this already in our previous video. And we found the complementary solutions that you see here for x1 and x2. Now, I want to point out these tell us that the natural frequencies of the system are omega 1 equals 1 and omega 2 equals 2. So 1 and 2 are the natural frequencies of the system. All right, we can now turn our attention to the non-homogeneous system. Let's go to a fresh slide. We're going to write this system as multiplying out x1 double prime equals minus 3x1 plus 2x2, and 2x2 double prime equals 2x1 minus 4x2 plus 120 cosine of 3t. So let's use as our trial solution for our particular solution C1 cosine of 3t, and for x2 C2 cosine of 3t. Recall, the natural frequencies of the system were 1 and 2. Here we're looking at a frequency of 3. So since this is a different frequency from those that were found naturally in the system, that's when we're allowed to proceed. Okay. All right, we're going to substitute these trial solutions into our system. So we get minus 9c1 cosine of 3t equals minus 3c1 cosine of 3t plus 2c2 cosine of 3t, and 2 times minus 9c2 cosine of 3t equals 2c1 cosine of 3t minus 4c2 cosine of 3t plus 120 cosine of 3t. All right, give us a little bit of room to work. We're going to clean these equations up by canceling out those cosine of 3t's. And we end up with 0 equals 6c1 plus 2c2, and negative 120 equals 2c1 plus 14c2. We solve the system and get that c1 is 3, c2 is negative 9. So in our particular solutions, we're going to replace c1 with 3, c2 with negative 9, and there we go. All right, let's put the pieces together. Here's our solution to the associated homogeneous system. Here's the particular solutions that we just found. We're going to add these together in order to get our general solution. Therefore, a general solution to the non-homogeneous system for x1, we get a1 cosine of t plus b1 sine of t minus 2a2 cosine of 2t minus 2b2 sine of 2t plus 3 cosine of 3t. And for x2, we get a1 cosine of t plus b1 sine of t plus a2 cosine of 2t plus b2 sine of 2t minus 9 cosine of 3t. Now, we want to solve for these coefficients, the a's, the b's, the a's and the b's. And so for that, we're going to impose our initial conditions. So the final step is to impose our initial conditions. Recall that x1 of 0, x2 of 0, x1 prime of 0, and x2 prime of 0 were all 0. So we're going to apply that to our general solution. The fact that x1 of 0 is 0 tells us that a1 minus 2a2 plus 3 equals 0. The fact that x2 of 0 is 0 tells us that a1 plus a2 minus 9 equals 0. The fact that x1 prime of 0 is 0 tells us that b1 minus 4b2 is 0. And the fact that x2 prime of 0 is 0 tells us that b1 plus 2b2 is 0. We solve these two systems and find that a1 is 5, a2 is 4, and b1 and b2 are both 0. We plug those values into our general solution, and our final solution is that x1 is 5 cosine of t minus 8 cosine of 2t plus 3 cosine of 3t. x2 is 5 cosine of t plus 4 cosine of 2t minus 9 cosine of 3t. Let's analyze our solution. We have a superposition of 3 oscillations in which the two masses move in the same direction with frequency of 1 and equal amplitude. Note it's the same direction since both our coefficients are positives, and equal amplitude since they're the same number of 5. They move in opposite directions with frequency 2 and with the amplitude of motion of mass 1 being twice that of mass 2. Note we know they move in opposite directions because one coefficient is positive, the other is negative, and we can see that the eta is twice that of 4. Finally, they move in opposite directions with a frequency of 3 and with the amplitude of motion of mass 2 being 3 times that of mass 1. Again, they move in opposite directions because one coefficient is positive, the other is negative, and the coefficient of mass 2 is 3 times that of mass 1.